Okay guys, so today we are going to start by learning a little bit about the field of aerospace, and this is going to lead us right into the project that we are going to do. So today we are just going to start by talking about aerospace, and the topic that we're really going to be focusing on is satellites. So if you were to look up the definition of a satellite, it would just say an object that revolves around another object. So does that mean the moon is a satellite? What do you think? Look at the person next to you. Is the moon a satellite? I would say yes, because the moon is an object that revolves around the Earth. So in that case, the moon would be a satellite. What about the Earth? Is the Earth a satellite? Is the Earth an object that revolves around another object? Absolutely, it revolves around the sun, right? So the Earth would be a satellite. What about you? Could you be a satellite? So your teacher's going to pause the video now so we can see if you guys can be satellites for a moment. So in aerospace, we're going to narrow down the satellite definition, and it's going to be a moon, planet, or machine that orbits a planet or star. So our moon would still be a satellite because it's orbiting around a planet, and Earth would still be a satellite because it's a planet orbiting around a star. But unfortunately, in this case, you would no longer be a satellite. So that's going to be our working definition of satellite that we use going forward. And we've talked about moons and planets, but we have not yet talked about machines. So when we think of satellites as machines, these are what we think of as being used for communication. And so what do these kind of satellites look like? The kind of satellites that are up in space that help us get our satellite TV or track our GPS systems. So your teacher's going to pause the video in just a moment here, and what's going to happen is she's going to pick some volunteers to draw satellites up on the board. So you guys are going to be given like 30 to 60 seconds to draw a satellite up on the board based on what you think a satellite looks like. So as you guys drew, satellites can come in many different shapes and forms. We probably have some ideas of what they look like, but honestly, they can be in a lot of different shapes and forms as they're orbiting around the Earth in space. So let's watch this quick video. Notice the time at the bottom of the video that shows how far after launch this is representing. So you can see that the solar panels actually don't start as deployed. They start all folded in so that they can fit into the rocket, and then they end up being deployed once it is launched into space and in orbit. So this is 16 days after the launch is when the instruments can start to be deployed so that they'll be used. So this particular satellite uses radar to look at soil moisture so that it can tell whether the ground is frozen or thawed and how much water is in the ground. And so what happens is the satellite passes over the Earth many different times, and then it was able to create this kind of full picture for us. So while satellites can be lots of different shapes and sizes, they all have some parts in common. So the main bus is going to be what is going to contain the primary electronics and computer modules for the spacecraft. So it's just the main part of the satellite. Antennas are a must-have on satellites because they communicate data back to the Earth. So we're putting satellites up there not to be just a hunk of metal in space, but because we want to gain information from the satellite. That's why it's going up there. And so in order to get the information from the satellite back down to Earth, it needs to have an antenna. It also needs to have a power system. So think about all of these instruments that are collecting data and moving on the satellite. In order for them to have power, they have to have a power source. And the power source for most of our satellites are going to be solar panels, just like you would think. And then it also is going to have instruments. So these are going to perform scientific experiments and measurements for our satellite. So again, we're not just sending a satellite up into space to send a hunk of metal into space and prove that we can do it. We actually want to gain information from the satellite itself. And the satellite, the main bus, does not actually give us any scientific data. So we have to put instruments on the satellite in order to get the scientific data, and that is powered through our solar panels and then communicated back to Earth using the antennas. So on the last video that we watched, we saw that there was a radar that was looking at the ground to collect soil moisture data, and that was an instrument that was used to make the satellite more valuable to people. So let's look at some cool satellite uses. So this is one of my favorite sites as a meteorologist. So satellites are actually really, really important in meteorology because they tell us information about the clouds and the weather that we wouldn't be able to get from just being here on Earth because it gives us a new perspective. So let me open this top loop, and it might take a minute to load. And while it loads, I just want to tell you guys that before satellites existed, so satellites started being used for weather purposes back in like the 1960s. And before that time, people really didn't know when hurricanes were going to hit because there was no way to see something that was out over the ocean. So we didn't have observations over the ocean, and so a hurricane would just hit and it'd be like, and it would be really damaging to a lot of people and property, right? But now that we have satellites, we can see and track where hurricanes are, how strong they are, where we think they're going to make landfall, when we think they're going to make landfall. And so satellites have really been revolutionary in scientific research when it comes to the weather. So let's take a look at the loop that you see here. So it's just going to keep repeating over and over again. So what you can see here in the middle, hopefully you can spot that out, is that you can see something that looks like it's smoking, and you would be absolutely right. So this is actually a wildfire that we can detect on satellite, and you can see the smoke, you can see where it's going, and you can see how it's spreading up here. And then if we continue watching the smoke as it goes up here, we can see it actually starts to loop back around through the mountains, and it gets caught on the side of the mountains, and you can see that it actually starts to loop back down this way. So it's a really good way for us to see different things that are happening in the atmosphere. I don't know if you guys can see this little swirly guy over here in the bay. So you can see the clouds actually look like they're swirling a little bit. That's something you would never be able to see from land. I don't know if you guys can see that. That is not a hurricane, it's just the clouds. And without getting too complicated in things, it's just the friction of against the land and what that looks like. You can see these are clouds actually over here. So this is the border of Nevada, and these are the clouds. So something that I want to point out to you guys as well is that as we get to the end of this loop, let me see if I can get it to stop. There. You see how it's dark here? So this is actually because this is a visible satellite image. So what is actually happening is there's a camera on the satellite that is taking pictures of this area. And so when it gets dark at night, it can't see the clouds and it can't take pictures anymore. So there are lots of different uses for satellites. Let's see some severe storms. And these might take a minute to load here because they're pretty hardy files. But you can see the storms, and the purple that's represented is actually lightning. So it has lightning detection as well as being able to take pictures. And because it's starting to get dark, you're able to see that this is actually a visible satellite image, so it's just taking a picture. But we can still detect the lightning. So you can see over here where the lightning is, you can see how it kind of looks like these clouds are like almost bubbling up. And that's what happens. That's how clouds form. And we can see lots of different types of clouds. So these are our thunderstorm clouds down here with the lightning. But in the back, these are kind of just spotty clouds. And those would not normally produce much rain, if at all. And let's see if we can get, there's a tropical storm. Maybe we can get it to load. There we go. All right, so this is a tropical storm over the ocean. So you can see that this is water that we're over. You can see that it's rotating counterclockwise. And if you look really carefully, you can almost see a little hole in the middle, and that's the eye of the hurricane. But this is really useful because then we can see how clouds are moving in different directions, different speeds. You can see these kind of wispy clouds and the really poofy clouds, and you can see things that are going in different directions than other clouds. And so this is all different ways that the satellite can actually be really, really, really helpful to meteorologists. And so you guys have access to this link. I'm not gonna lie, this is like really addictive for me personally. I know I'm a weather nerd, but to like click through and just see some of the things that are like, these are actual images from satellites. So this isn't something that's generated by a computer. This isn't something that's taken by a storm chaser or anything like this. These are actual satellite images. So this storm right here actually became tornadic, which means it produced a tornado. So you can see it start from like a little tiny baby storm and then grow into this massive storm. You can see these clouds back here that almost look like they're kind of wavy. That's really normal. You can see the wavy clouds here. You can see how this is bubbling up. So you know that's like the center, the hardiest part of the storm. So this is, this is really cool to me. But hopefully you guys now can at least see and understand that there are some really cool purposes behind satellites. So let's go back. You are actually going to build a satellite for your project. So let's think and look at this video for wanting to build a satellite.
Say you want to send a satellite from Earth all the way to Mars. Now it's got to get there without running out of gas, malfunctioning, or otherwise causing trouble. And if that's not enough, it's also got to sample things and send the results back to Earth. Now, that being said, it seems obvious that you can't just go building satellites all willy-nilly. Satellites are expensive little things, and you need to make sure that all your plans will work before you run out of money. This is why, before building anything, scientists and engineers hold what looks like an endless series of meetings, phone calls, telecons, tag-ups, and get-togethers, culminating in what's known as a design review. Take, for example, the MAVEN spacecraft. Now, it's a great idea for a satellite, one that studies the upper atmosphere of Mars, but, of course, it's not good enough just to have a great idea. It needs to be reviewed, just like anything else. At this review, a whole lot of other smart people take a good long look at the design, and hopefully they decide they like it. If all goes well, they think that everything makes sense, the budget is in line, there isn't substantial risk involved, and now we can move on to the next step. And once you've finished, you'll finally be able to get all the data you wanted without any trouble.
On Canvas, you guys are going to go get your Build a Satellite worksheet. So if you just go to today's date, to today's information, you're going to see a Build a Satellite worksheet. It is going to be a Word document, and you should save a copy because you will have to make edits to it. And this is something you guys are going to turn in later. So please go onto Canvas right now and download your Build a Satellite worksheet, save a copy of it, save it to Freshman Survey of Engineering Unit 2 Aerospace folder that you should now have in OneDrive so that you guys can access it because we will be using it for a couple of days. So when you pull it open, if you're still pulling it open, that's okay. Take your time to pull it open, and I'm just going to start talking about the worksheet itself and kind of what your goals are going to be for this project. So this is what it has at the top of your Build a Satellite worksheet. You are going to include your team name and your team members. And this is going to give you your objective for your project. So your task is to build a satellite model out of available materials. Your satellite must include as many scientific instruments as possible to return the greatest science value while staying within the size. It has to fit into an oatmeal container. And it has to have mass constraints as well. It can only weigh up to 60 kilograms total, including all of the science instrument and the power systems, the solar panels. So we are going to use the data in the table to determine which instruments and how many of those instruments to include on our satellite in order to achieve the greatest science return. The only required science instrument is a communication antenna. So you guys are going to build a model satellite, and we want it to be effective and scientifically valuable, right? Because we don't just send hunks of metal into space. So if you go to the satellite instrument data table that looks like this, it is going to give you a list of things that you can include on your satellite. A couple of things you have to remember is that your satellite must have a communication antenna. So you'll see here at the bottom, there's a high gain and low gain antenna. And so these don't add any sort of scientific value because they just send information back to Earth. So remember, this is really important because we don't just send hunks of metal into space just for the fun of it. We need to collect data using these instruments. And then in order to get that data back to Earth, we have to have an antenna. So you do have to have either a high gain or low gain antenna on your satellite, and that does contribute to the weight. Remember that you have a constraint of 60 total kilograms. You don't actually weigh anything, you just use everything here from the table to determine your mass. And you have to choose which antenna, and you do have to have one, okay? You also have to have a power system. So your power system are going to be your solar cells. And now it says it's 1 kilogram, and obviously you don't need any solar cells to power your solar cells, duh. And they don't provide any scientific value, so they're not gonna make your scientific value of your satellite like super great, but you need them to power all of your instruments. So when we send our satellite up into space, in order for our instruments to actually collect data, they have to have power. And so that is where our solar cells are going to come into play. So when you start to look at some of your instruments, like say the high resolution camera, it captures close-up images, kind of like what we were looking at for the weather loops that we were seeing. And it weighs 25 kilograms, and it needs 2 solar cells to power the high resolution camera. And so that means that if we wanted to include the high resolution camera, then we would also need to include 2 solar cells, because our high resolution camera can't do anything unless it has a number of solar cells that it needs in order to be powered on to take the pictures, right? If we wanted to use a gravity probe to measure gravity, then that weighs 12 kilograms and it needs 1 solar cell. So say we had a high resolution camera and a gravity probe, then we would need a total of 2 plus 1 solar cells. So we would need a total of 3 solar cells in order to power our instruments. You'll see that some of them actually have half a solar cell. So remember that we can't make half a solar cell. So say that you had these top 4 instruments. So say you had a high resolution camera, a context camera, a gravity probe, and a magnometer. okay? So that's 2 plus 1 plus 1 plus 1/2 is going to be 4.5 solar cells needed to power. But you can't make half a solar cell, so you would have to include 5 solar cells in order to power all of these instruments. And the reason that's really important to know is because it tells you how many solar cells you need, and it also tells you that you are going to have a certain amount of mass associated with your solar cells. And so if you need 5 solar cells, then you need to remember that that's going to take up a total of 5 kilograms of your mass. So remember that it has to weigh less than 60 kilograms. So on the next page, you are going to have an empty instrument data table where you guys are going to list your instruments, list the mass of each, the number of solar cells it is requiring, and the science value. And you need to remember that this total mass needs to include your solar cells and be less than 60 kilograms, okay? And the last thing that I want to talk about is the science value. So you want to get as high of a science value as possible. So remember that a higher science value means that you're giving more data, more information back to Earth, which means your satellite is more useful. And so your science value is in this last column over here. You can see that most of them are 1, but a couple of them have a scientific value of 2. So a lot of the ones that have a higher scientific value also have a higher mass. So you're going to have to make some decisions as to what you want to include on your satellite, but try to get as high of a scientific value as possible. And if you're going to include, like say you want to include many laser altimeters, then you need to tell me what they're going to be used for and how they're going to be different. Okay, so you can't just say, oh, well, it doesn't weigh much and it has a high science value, so we want to include 8 laser altimeters. Okay, well, if you're going to have 8, we don't need 8 times the same information giving back to Earth, right? So in general, you should only have 1 of each instrument unless you have personally done research to say, I can have this kind of laser altimeter and this kind of laser altimeter, and therefore I want 2 of them. All right, so in general, you should only have 1 of each instrument unless you have specifically given me a reason why you're going to have more than 1. So in your teams, you guys are going to get together and you are going to fill out this data table. So remember, your constraints are you want a high science value and your mass cannot be greater than 60, and you have to have an antenna and you have to have solar cells in order to power all of your instruments. You also have to get teacher approval. So to start building, you are going to need a completed instrument table, and you are also going to need drawings of 2 different views of your satellite. So you need to sketch out what you think you want your satellite to look like. You only need to do 1 sketch as a team, and then you guys can send it to each other. So remember how we talked about shared documents before? I recommend opening up the Build a Satellite worksheet and sharing it with each other. You only have to do 1 for your whole team, and then everyone can individually turn it in, okay? So put it all into a shared document so that you guys can all edit it. Choose someone who's really good at drawing. If you want to draw on the iPads, you guys can absolutely use the draw feature. A lot of people do that. If you want to draw it on paper, then take a picture, upload it into this space, and that will also count as your drawing. But you need to sketch out what you think you want your satellite to look like, and you also need to come up with a list of materials. So in order for you to start building, then I am going to need a list of materials of what you think you want to use. So I'm not just going to send you out with unlimited materials and say, hey, go have fun, build things. If it doesn't go well, oh well. It's important that you are using your resources wisely. And so that means that you should have a plan and then be able to execute that plan. And that's why your teacher is going to require approval of all of these things before you start building. Okay, so make sure that your pictures are clear and labeled, and make sure that you have a list of your materials that you want to use. You can always add things onto that later, but you guys should at least have a starting point so that when you go in there, you're not kind of spinning in circles saying, where do we start? You have already talked through it. You've already come up with the plan. This is the engineering design process, and it's something we're going to do multiple times in this class. Okay? So make sure that you get your teacher approval before you start building anything.
Say you're somebody who wants to build a satellite to go around Mars. You've done lots of hard work, your designs are approved, and so you think to yourself, great, I'll just whip it together like that office chair I bought last week. Unlike your chair, however, a satellite has to survive in space, where it's extremely hot, extremely cold, and just plain dangerous to nearly everything. So, as you might imagine, it's a little more difficult to put a satellite together. To give you an idea, let's take a look at a bolt on the Maven spacecraft. Now, if this was a screw on your office chair, you'd find a screwdriver, sit down for about 15 seconds, and be done with it. If you want to put the same bolt under Maven, however, it's slightly more complicated. You have to test the bolt, get the bolt approved, clean the bolt, make sure it's the right bolt again, build scaffolding so you can install it, get the scaffolding approved, check the size, check the fit, and finally put it in carefully with a torque wrench. And once you've put in all the screws, you have to test the entire satellite to make sure all of them stay put. Now, this all may seem a little silly, but if you've got screws falling out of something that's millions of miles away, you've got trouble on your hands, and nobody wants that. And what's more, the bolts are the easy part. Satellites are complex things filled with tons of electronics, so you can only imagine how much work it takes to put those together. So, while it may take a little more time and a few more people than an office chair, it's definitely worth the effort. And once it's built, the spacecraft can get onto its real job without having problems on the way.
In order to make sure that our satellites are actually going to be ready to be launched into space, they go through something that's called a shake test. And this is something that's actually done in real life, and we're about to watch a video of it. So as it is launched in the rocket from Earth into space, it undergoes a lot of G's, or a lot of gravitational acceleration is what it's called. And you need to make sure that the satellite's going to be able to withstand that, because if you invest millions of dollars into something and then you're not able to fix it and it breaks and something happens, then those millions of dollars are just wasted, right? So here is a way that they actually test the satellites.
Hi, I'm Randy Stark, and this is your Building Curiosity update. We're here in the Environmental Test Facility at JPL, where Curiosity is going through a series of random vibration tests. This test is like putting Curiosity through a major earthquake. It's going to shake it both side to side and up and down. You'll notice that Curiosity is actually in its flight configuration, which is upside down.
Three, two, one. We have ignition.
These tests will ensure that the hardware was not only built correctly, but assembled and will survive the launch conditions. Next will be system thermal vacuum test, where we put Curiosity in a large vacuum chamber and simulate the environments, both hot and cold, that Curiosity will see during its journey to Mars and also during its life on Mars. It sure seems like we're putting Curiosity through a lot of abuse, but the more testing we can do here on Earth will ensure a safer journey on the way to Mars and a longer life once we get to Mars. This is Randy Stark, and this has been your Building Curiosity update.
So you guys are actually going to be doing a shake test yourselves. So if you remember, let's see here, let me go back to this page here. It says that it needs to be able to fit into an oatmeal container. And that is because we are going to put your satellite into an oatmeal container and shake it for about 30 to 60 seconds to make sure that it can withstand the launch into space. So you need to make sure that your satellite is built sturdy and within the size constraints, because if you build an awesome satellite, but it doesn't fit into the rocket, then it is not worth anything, right? And if you build an awesome satellite and it fits into the rocket, but it breaks on the way up, then your satellite also isn't worth anything. So this is why you guys are going to have to fit your satellites into an oatmeal container, and it will have to withstand the shake test as well. For today, I want you guys to do a little bit of research on satellites and start looking up some satellites that are really cool. So I want you guys to go to eyes.nasa.gov, and we're going to click on Eyes on Earth to see some really cool satellites. So If we go to eyes.nasa.gov, you can see a bunch of different options. Eyes on Earth. Here, you're going to see the little satellite guy. Go ahead and click on that, and it should pop up. And here, you can see satellites that are actually rotating around the Earth right now. And so you can use your hands, you can rotate the Earth, you can figure out, oh, there's Arizona, that's where we live, that's the United States. You can see different weather systems. And what's really cool is you can click on a satellite and it will zoom in and it will show you the satellite, okay? And here, you can actually move it around, you can zoom in, you can zoom out to get information on the satellite. You can get ideas about what things look like, what's the layout of the satellite. You can, I just push the little up arrow down here where it says GPM, the name of the satellite. It tells you how long it's been in orbit. There are some satellites that have been in orbit over 20 years, so try to find those ones. So it'll tell you a little bit about the satellite and what its purpose is. So this particular satellite tries to measure rain and snow worldwide, and the mission advances the understanding of water and energy cycles and improves the forecast of destructive storms. Pretty cool. Related to weather, just like we talked about. And you can see it's moving, it's rotating. So at any time you can push back and it will take you back to all of the satellites, and you can click on another one. Here's the S-map. That's the one that we were looking at earlier that measures soil moisture. Oh, maybe it'll load. There we go. So it'll zoom in and you can see that's the one that we saw in the video. You can see the little antenna for the radar, and that's the one that was measuring soil moisture. Let me go in, and that one's been in orbit for 7 years, and it talks about what the purpose of this satellite is. So it's actually really cool for you guys to look at. You can zoom in, you can play with it. If you click up on Visible Earth, you can actually use different things to, like what the Earth looks like. So the Visible Earth is going to show all of our clouds because it's just a picture of what Earth looks like. But you can try air temperature. So you can see that we live somewhere very, very hot, right? You can see air temperature. There's all sorts of things that you guys can click around and play with. So I want you guys to be looking at different kinds of satellites, getting ideas, and with any time that you have left in the class, you may work in your groups to start completing your Build a Satellite worksheet. If you have any questions regarding this project or what it's supposed to look like, go ahead and talk to your teacher. So sit with your groups, look at some of the satellites on this page, and then begin working on your Build a Satellite worksheet.